Hi, everybody, and welcome back. I hope you had a good breather, and I hope you are ready for a talk by Ben Stappers. So Ben, I will introduce you as one of the great gurus in pulsar astronomy. He has a wealth of experience, and together with his Stratton team, I believe he is probably one of the most data-intensive users on the Meerkat telescope. And this is because he is leading the team that searches for new pulsars and transients such as the FRBs you learned about today. And you will likely get a flavor of this in his presentation, that such efforts do require a small mountain of GPUs and some clever computing strategies. And boy, does he have experience in doing just that. He has previously worked on the design for many other telescopes. He worked on the LOFAR instrument, and after Meerkat, is also looking to play a central role in how we gear up to the square kilometer array and how we will use that to, again, study and detect pulsars and fast radio transients. So for now, Ben is currently a professor at astrophysics at the University of Manchester. That's where he's calling from today. He originally was born in New Zealand and then received his PhD from the Australian National University in Canberra before he started working for a decade in the Netherlands. So that was his shift to Europe. His CV boasts over 100 Pi research publications and many other numerous awards. And currently his research centers on searching for pulsars and fast radio transients, like I've mentioned. So he thinks about how we use them as probes of physical theories and probing the properties of the universe. So currently, he's leading the team working on Meerkat, and that's what we'll learn more about. Welcome, Ben. I hope you'll have a good time, and we're really looking forward to your talk.
Thanks, Marissa. That's a very generous introduction. And hello to everybody out there. As always, it's slightly odd to be speaking to the void, but I hope to bring some of the enthusiasm we have for this subject to you today. So as Marissa said, what I'd like to talk to you about is an introduction to how you would search for pulsars. And so the outline of my talk is going to be split into two halves, really. I'm going to spend the first half talking about technical approaches, talking about the techniques that we use, such as single pulse techniques, using the fast Fourier transform, and using the fast folding algorithm to try and find pulsars. And then I'm going to talk a little bit about where we want to look. So where do we think we should best spend our telescope time? So it's a really hard choice to make, and so we'll be talking about that a little bit. And then we'll come to the why. Now, you will have heard some of the why already from the great presentations that you've had today, but I'll touch on a few other topics that I think haven't yet been covered for why it's useful and interesting to find new pulsars. So here's just a quick reminder about single pulses, and you'll recognize the graph on the right, which I have leveraged, shall we say, from Marissa's presentation today. And you will see that single pulses are the way in which pulsars were originally discovered by Jocelyn Bell Burnell all those years ago. The single pulse search relies on the instantaneous sensitivity of your telescope. So you basically need to optimize the sensitivity of your telescope, because what you're trying to do is detect one of these pulses in the few milliseconds for which it's actually on. How successful a single pulse search will depend on the range of energies that you can expect from these pulses. So you may have heard a little bit today about giant pulses, for example, which are many thousands of times brighter than the average pulse profile. And if your source gives off giant pulses, then it's a really good way to try and discover it. In fact, about 2 decades ago, some theoretical work was done which recognized that about 1/3 of all of the pulsars that were known at the time could have been discovered via their single pulses. And so it's a viable method to try and find new sources. And interestingly, that same group who worked this out, they went and they searched through data that they had recorded and stored, and they found a whole class of new objects. And these objects actually don't give off pulsed radio emission every time the neutron star rotates, but they give off a pulse maybe once every few minutes or even a few tens of minutes. And so these pulses are actually really quite bright, and the sources are mainly off. And so this is the only way to find them is by looking for the single pulses. So how do we do this in a practical sense? Well, you can be brave and go and sit outside, wiring up your own telescope and running a chart recorder. But of course, things have moved on a little bit since then, which is lucky for us. And here is an example of what I was talking about the pulse energy. So this is a known pulsar with the name B2020 plus 28. And in the top panel of this graph, you can see the shape of the average pulse profile. So what the intensity looks like if you average many hundreds of pulses together. In the bottom panel, what you can see is the individual pulses plotted as a grayscale, or in this case as a yellow scale. And you can see that sometimes the individual pulses are extremely bright, a lot brighter than the average. And so they can often be detected more easily using a single pulse technique. And here is the example of the so-called RRATs, these rotating radio transients that I mentioned. And what you can see in this plot is a plot of time against dispersion measure, and you've encountered dispersion measure earlier today. And you can see these little regions of brightness here, and these correspond to detections of single pulses from these new type of sources. So how do we search for these single pulses? Well, on the left-hand side, I'm showing you a section of a flow diagram, which says we get the raw data from the telescope. And this sort of orangey colored plot that you can see just below that is showing you actually a very bright source. Each of these yellow lines curving down like this is a pulse from a pulsar. And you can see the classic curvature, which is proportional to 1 over the observing frequency squared. What you can also see here is lots of wiggles and other things that correspond to the radio frequency interference that Marissa has introduced you to earlier today. And so the first stage in all of this analysis is to remove the radio frequency interference, and that gives you something more like what you see in the bottom plot. Then what we need to do is we need to do dedispersion at multiple trial values for the dispersion measure. So you've learned about dispersion and dedispersion, but in this case of a search where we don't know what we're going to find, we don't know in advance what the dispersion measure of the source will be. And so So first, let's just talk about the radio frequency interference. And just to remind you, I've taken exactly the slide that Marissa showed you earlier today, in which you can see these features due to the global positioning satellites or the GSM, your mobile phone, for example. And these can all have an influence on the signal. And if we don't remove them, then these very weak new objects would not be able to be detected. Here is the dedispersion that you learned about earlier as well. And you can see here the time delay is proportional to the dispersion measure and then 1 over the frequency squared. And then you can see these slopes that we need to correct for, depending on the frequency that we're observing with. In the plot that you see in front of you now, what we've got here is the distribution of electrons in the galaxy as viewed from Earth. Okay, so if we were to take a sight line through the galaxy in any direction, this is the total number of electrons, free electrons, we would expect to see. And so this gives you an idea of where you think the dispersion measure will be greatest or least. Okay, so in the center of the galaxy, in the galactic plane, you would see lots of electrons because that's where all the gas is located, for example. And so if we look in that direction, we would expect a very large dispersion measure. But we can't predict accurately what the dispersion measure will be in advance. because we don't, although we do have a model for what we think the electron distribution looks like in the galaxy, the model is not perfect. And so we need to search over a wide range of values for this dispersion measure. So we need to do dispersion measure trials, and here is an example of what difference that makes to the detection of a single pulse. So if we choose to look at the data at dispersion measure 0, and here I'm showing you two plots. One on the left-hand side is what we call a dynamic spectrum, and you can see we have frequency on the y-axis and time on the x-axis, and the color scale is just the intensity of the values in each pixel. And then the plot on the right is if I just collapse all of that in frequency space. So I de-disperse the data at DM0. So I move all the frequency channels. In this case, I don't move them at all because, of course, it's DM0. But if I was doing other DMs, I would move all of the frequency channels, and then I would add them all together. And that would give me the plot on the right-hand side. So here is what we would get if we did DM0 for this particular new source that we've discovered. And these are real data taken with the Meerkat telescope quite recently. So what happens if we go to DM100? And believe me, we need to step in smaller steps than this, but I'm not going to make you go through all of the 5,000 plots or so. Again, DM100, we're still not seeing any evidence for any signal. So it's clear that our pulsar does not have a dispersion measure of 100. Now, if we get to a dispersion measure of 190, what you can start to see is, if your eyes are good, you might be able to see a little hint that there's a streak of darker colored pixels here. Okay, and that streak is not straight. It's still got some curvature in it, which means that we do not have exactly the right dispersion measure. However, when we add all of the data together, we see that we're starting to get a little peak here, indicating that we might have a real source and that we're getting close to the true dispersion measure of this pulsar. And then for comparison, here is the real dispersion measure of the source. And you can see we've got a clear, sharp pulse detected here. And again, depending on how well this is coming across on Zoom, you should hopefully be able to see a gray line lined up with my cursor here at around about half a second into the file. So we have to try all these different dispersion measures if we're going to try and find new pulsars via this single pulse technique. And Marissa already mentioned something to you about fast radio bursts. And this is exactly the way that you would find fast radio bursts as well, except we would typically have to search out to dispersion measures of many hundreds and thousands to be able to find those. So how do we actually do the single pulse detection? Well, we've tried all of these different dispersion measures. So how are we going to decide whether at each of those dispersion measures do we have a signal of some significance? So the thing we will do is we'll take a region of this data and we will calculate some statistics. We'll calculate the root mean square, we'll calculate the mean, and we'll calculate maybe even the higher order statistics. Then we'll use that and compare it to the amplitude of the signal. So we'll set a threshold at an appropriate level given the number of trials that we're doing and the statistics of the noise in the data. So for example, in the search that we're doing for fast radio bursts and new transients, we set this threshold at something we call 8 sigma. So that's 8 times the standard deviation of the noise. And this might sound like a high number. You might say, well, why is a 3 sigma detection not significant enough? It's because we are doing so many different trials. So each time you use a different dispersion measure, you are effectively trying to find a signal. And so that affects the statistics of your detection. And ultimately, this is the sort of plot that you might be faced with after your computer has done all of these calculations, it will spit out a plot like this, and you will look at it and you will try and make a decision as to whether you think this is real or not. And you can see up in the top here by signal to noise ratio, which is basically that threshold divided by sigma. This is a signal to noise ratio of 14. And so we thumbs up, this looks like it's a real signal. So that was how we'd search for pulsars using the single pulse search technique. It's quite relatively simple compared to how we might search for pulsars using the fast Fourier transform. Now, I believe that you've encountered something like the DFT before. This is basically just an implementation of the DFT, but instead of in a spatial domain, we're now doing it in the time domain. So what we're taking advantage of here is the fact that pulsars are periodic objects. They rotate with a fixed period, okay? And so if you do a Fourier transform of something that has a regular pulse in it, then you're going to find a feature in the Fourier domain at 1 over the separation of those pulses, okay? So you're going to get what we will call frequency, and I know that's confusing because we've been talking about sky frequency now, but now I'm talking about rotation frequency. And so we can get the frequency, and then when we have the frequency, we just invert that to get the pulse period. So how do we do the searching using the fast Fourier transform? Well, the start of the whole process is very similar to the single pulse search that you've already encountered. So all of the steps, the raw data from the telescope, cleaning out the RFI, those will all be the same. And then we're going to do the dedispersion. So here again, we don't know what the dispersion measure is at the start. So we need to try all sorts of different values for the dispersion measure. And for each of those, we're going to get a time series like the one shown in blue below here. Okay, now I've only shown 4 seconds worth of data here. Normally we would be observing for many minutes, but this is just to demonstrate the data. And so the next step is that we want to take the Fourier transform of every single one of these dispersion measure trials. Okay, so we're going to take the Fourier transform, and what you'll get now is you'll notice we've changed from time in this axis here to frequency, and then we've got power in arbitrary units here. Okay, and what you can already see is there's a hint of some feature at these different locations. Okay, and so that could correspond to the spin frequency or the rotation frequency of our pulsar. You'll notice, though, that there is some curvature here, which it goes up in power level as we go to shorter and shorter values for the frequency, which corresponds to longer and longer periods. And this comes about because our system is not stable. On long time scales, our baseline might wiggle for whatever reason. It might be due to radio frequency interference that we didn't remove. It might be due to sources appearing in the far side lobes of our telescope, or anything like that. And so this we call red noise, and we need to remove this red noise because you can imagine if I stuck my threshold at some height here, then I would not see any of these features because the red noise is confusing my statistics. So what we then do is something we call dereddening. And dereddening, you can see, has flattened out this noise, okay? So we've fixed the mean of the data. And now you can clearly see these different peaks here, and you'll notice that the peaks appear to be equally spaced. So that brings us to the next stage in this analysis, and that is to identify these peaks. And similarly to how we did it for finding single pulses in the time domain, we're going to do something similar in the frequency domain. So here we'll have a threshold which we'll determine based on the noise, so the noise in this region here, and then we'll put in a threshold. And anything above that threshold will become a candidate pulsar. Okay. And here you'll see we have these harmonics. And the harmonics arise because the pulse duration is much, much shorter than the space between the pulses. Okay, so we call this the duty cycle. The duty cycle for pulsars is usually something like 5 to 10%. That means for 5 or 10% of the time, you receive radio emission. The rest of the time, you receive nothing. And the Fourier transform is based around the idea of describing your data as a combination of sinusoids and cosines. And what happens is that the number of different, oops, sorry about that. The number of harmonics that you see relates to the frequency of the sinusoids that are needed to make up the shape of your pulse profile. And so these harmonics tell you not only that you potentially have a real signal, but they also tell you the true frequency of the rotation of the source. So the next stage is that we take that best estimate of the rotation frequency of the source, and we take the best estimate of the dispersion measure, so where we get the highest value for the signal, and then we take that data and we fold the data with that dispersion measure. We dedisperse the data with that dispersion measure, and then we fold it with that pulse period. And I think you heard about folding earlier today from Marissa. And in this case, you get a plot like the one I show you here, and this is a candidate plot. And the candidate plot is such that you can see this is pulse phase and this is time. And you can see the signal is pretty constant. There's still some RFI in here that's affecting our data, but we can be pretty sure that this looks like a pulsar. We've got a nice peak here if we look at dispersion measure versus signal to noise. And so we've got all the indicators that this is a new pulsar. It might also be necessary for us to do some more radio frequency cleaning of the data. And we may also need to do some machine learning. And I won't have time today to talk to you about machine learning, but it's becoming an incredibly important part of searching for pulsars and for fast radio transients, because we get many, many, many millions of candidates. And so looking at those by eye is impractical, to say the least. So we've done single pulse searching, we've done Fourier transform searching. Now we're going to talk about what's called the fast folding method. So why do we need another method? What is wrong with the Fourier transform method? Well, you actually already got a hint of that when you looked at the issue of the de-reddening, okay? So the red noise that we have can affect our ability to detect the pulsars with the longest pulse periods. So those long period pulsars that would have been at the low end of that frequency plot that I showed you, they will be affected by the wiggly baseline. And you can see that in an example just here, and we'll come to that in a moment. And so the fast folding algorithm gets around that. The other thing is that most pulsar search algorithms only look up to the first of 16 of those harmonics that I showed you before. And that can affect your ability to recover the signal from the pulsar. This fast folding algorithm actually recovers all of the signal that is present in the data. As always, we start with the same methods that we had before. We start with the cleaning of the data, and then we do the dedispersion. And as I mentioned, if you've got some RFI that you haven't cleaned or whatever, that's not possible to clean out of your data, or, for example, there's some change in the conditions that give you this increase in the baseline, you need to remove that if you're going to try and detect your pulsar. And so you can use something like a running median filter, and you run that over the data, and this will give you a nice, smooth baseline. So the first thing we'll do is we'll smooth out our data using this running median filter. So the next step we do is we do the fast folding itself. And what does fast folding mean? It means that it's a clever way of folding the data at many hundreds of different possible pulse periods. Okay, so it does a similar process to the pulse folding that you heard earlier from Marissa, but now we talk about doing many hundreds of different ones. And it does some clever tricks. It realizes that this problem is partially recursive, and so you can reuse some of the analysis that you've already done, hence the fast aspect of it. And what you end up with now is, instead of the frequency versus amplitude that we had before, now we have a period, and then we have a width. And what is this width about? Well, the width is that if we're trying to detect the signal, we want to match the duty cycle exactly to catch all of the signal. And so we try and convolve the data with lots of different widths. And so in this particular case, the pulsar stands out in the middle here with the correct period and the most appropriate pulse width. And so, in here where I've put down my threshold. So again, you would use a threshold similar to what you'd used for both the single pulse detection and the fast Fourier transform detection method. And as before, we want to go and optimize the data. So after we've got an initial value for the fold period and the width, we might go and reanalyze the data, trying to improve our analysis, removing a bit more radio frequency interference. And then again, we need to pass it to a machine learning classifier. So this is a quick tour of the 3 different methods that are usually used for a pulsar search these days. Now, because of the advantages and disadvantages of all 3 of the different methods, it's prudent when you're searching for pulsars to try and use all 3 if you possibly can. However, of course, you may be computationally limited. You might not have enough computing power in order to be able to do that. And so that's maybe a choice you have to make. I'd also note that the fast folding algorithm, while it's existed all the way back to the discovery of pulsars, the first paper on the fast folding algorithm was in 1968, and pulsars were already discovered. It was discovered in 1967. Famously, actually, the person who wrote this paper is also the person who found the giant pulsars from the Crab pulsar. And so this algorithm has existed for a very long time, but it got lost when the fast Fourier transform came along. And it's only recently that it's being rediscovered and reused. So now on to where to look. So where do we spend our telescope time? So there's 2 different views of our galaxy here. On the left-hand side, it's an ATOF projection, again, as if we were looking towards the galactic center. You can see the central region is the galactic plane, and all of the black dots that you see are pulsars that we know about, pulsars we've discovered. Some of them you'll see have got circles around them. Those are the pulsars located in binary systems. You'll notice a collection of sources here, for example. That's where the Magellanic Clouds are located. But basically, you can see that the vast majority of the pulsars that are known are in the galactic plane. And that's mainly because they're young and they're associated with star formation, and stars tend to be born in the galactic plane. If we look at the top-down approach here, you can see the spiral arms, or a model of the spiral arms in our galaxy, and you can see the white crosses here are the locations of all of the known pulsars. So the black circle up here, that is the location of the sun, and here is the center of our galaxy. Okay, and you can see that the vast majority of the pulsars that we know about are in the nearby neighborhood or in this inner quadrant as we look towards the galactic center. So the question is, where do we go and look? We can go all sky. So we can try and do a pulsar search across the entire sky. Now, the advantage of that is that it gives you a completely unbiased view of the population of pulsars in the galaxy. And so it's a really good thing to do if you can. The disadvantage is that it takes a long time, and in many locations you'll find nothing. And so are you optimally using your telescope time when you plan your survey? Because a lot of the time you're just pointing where there's very little chance there'll actually be a pulsar. The other option is that you can do a targeted survey. You can choose specific regions or objects to look at because you think that there might be a pulsar located there. And we'll come back to what those locations might be in a minute. The disadvantage is that it might give you a biased view of the population. You're only looking in the places where you expect to see things. And so maybe you'll only find the types of objects that you already know about. The advantage, though, is that you could optimally use your observing time, increasing your sensitivity and increasing your time per pulsar discovery. Here is an example from this beautiful image from Meerkat of the galactic center region. You can see a number of supernova remnants. And as you know from earlier today, you expect pulsars to be, young pulsars at least, to be associated with these supernova remnants. And so you might look at this image and go, aha, I expect that in these locations, the supernova remnants, I expect there to be a pulsar. So I will spend my observing time looking there. But of course, then you're probably only going to find young pulsars. You're not going to find any of the millisecond pulsars, for example. Another possibility is that you could try looking in globular clusters. So globular clusters are these enormous conglomerations of millions of stars in our galaxy, where we know that there are, in some cases, many dozens of pulsars. And so we can point at those objects and find new pulsars. We could also take advantage of the fact that we know that when pulsars are located in dense environments, they interact with those environments and they generate what are called pulsar wind nebulae. And these pulsar wind nebulae shine very brightly in very high radiation photons, up to TeV, tera electron volt photons. So they're incredibly energetic. They're high energy gamma rays. And when these can be seen in our galactic plane, and they can also be pointers to where pulsars are located. And last but not least, the Fermi gamma ray satellite has identified many, many locations where there is a strong indication of a gamma ray source. And we know that lots of these gamma ray sources are associated with pulsars. And in particular, they're associated with the very fast spinning millisecond pulsars. And so again, we can use this information from the Fermi telescope to guide us as to where to look. But again, we're biased because we're most likely to find energetic young pulsars or millisecond pulsars. So we've got this choice to make between targeted and untargeted searches. The next question is, why should we search for more? You've probably heard today already that there are something like 3,000 radio pulsars known. And so why do we want to search for any more? What are they going to be useful for? Well, there's a whole range of really exciting physics that we can do with radio pulsars. We can study the emission physics, the very high magnetic field strengths, the very strong currents that are present. The way that they emit is still unknown. And so there's a lot we could learn from finding more extreme systems. We could be interested in studying the binary and stellar evolution. How did these objects form? Where did the stars come from? How do those stars form? What does that tell us about our galaxy? What does it tell us about the history of star formation in our galaxy? We can also use them to study gravity. And I think Marissa has talked to you already today, and you've done an exercise yourselves on the double pulsar, which looks at the relationship with gravity. We can also understand the physics of supernovae. Supernovae are incredibly important in terms of the fact that they return a large amount of material back into the galaxy for further use in the making of stars and the like. And of course, there's the super dense matter at the center of these neutron stars that is of great interest to physicists who want to understand the properties of neutrons and other atoms. So just to remind you, here's the famous period derivative diagram where we're able to place all of the known pulsars and arrange them into groups. And you can see in the left-hand corner here, there are the young pulsars. These are the rapidly spinning objects. They are associated with supernova remnants, so they're just been born. You can still see the supernova remnant. Up in the top right-hand corner, you can see the so-called magnetars. These are objects which have these really, really strong magnetic fields. And a few of them are now known to emit in the radio. In the middle here is where all the normal pulsars live. Just below that is where the double neutron star systems exist, like the double pulsar that you worked on. And we sometimes call this the Nobel Prize zone. And then down in the left-hand corner here, you can see, again, lots and lots of these very rapidly rotating objects called millisecond pulsars. They're usually located in binary systems, hence why they've got the circle around them. They're very stable, and they make the best clocks in the universe. So let's concentrate first on these millisecond pulsars. What can we use them for? We can use them to potentially detect gravitational waves. Even today, you will have heard that there was a press conference about LIGO, Virgo, and Cargo detection of the merger of a black hole and a neutron star. This is an amazing result, and it shows us the power of gravitational waves and what we can learn from them. We can actually, not only are the neutron stars involved in generating gravitational waves in these merger events, but we can actually use the neutron stars that make up pulsars to try and detect gravitational waves from the merger of supermassive black holes early in the universe. So what happens is that we can use the arrival time of the pulsars on the Earth to measure apparent changes in the distance between the Earth and the pulsar due to the presence of the gravitational wave. And we probe frequencies that are in the range of 10 to the minus 8 to 10 to the minus 9, or sometimes we call these nanohertz. And so they were very sensitive to the orbital periods of two black holes in the early universe. So just to show you what this is like, if you're familiar with how the LIGO and the Virgo detectors work, you can think of the Earth and the two pulsars as being like the arms of the gravitational wave detector, the LIGO or Virgo in this case. And so the space-time is distorted by these orbiting black holes. That distortion affects the arrival time of the pulsars at the Earth, and that we can look for that and try and make a detection of the gravitational waves. And here's a little video that just gives you an idea of what this is, what this means. If we have two galaxies early in the universe and they merge together, and we think those galaxies are likely to have black holes at their center. And so when those two galaxies merge, the black holes will start to orbit each other. And as they orbit each other, this green region shown here corresponds to the emission of gravitational waves. and those gravitational waves will travel across the universe into our own galaxy, and then affect the space-time between at the location of the Earth. And so the pulsar to us will appear to have either sped up or slowed down, depending on what the phase of the gravitational wave. And we can compare that to lots of other pulsars to make sure that it's not just something wrong with that actual pulsar, and then that will tell us about the presence of these gravitational waves. And why is that important? Well, it's important because we think that the universe, the structure in the universe that we see, and the galaxies that we see around us now, formed via this process, this so-called bottom-up process, where galaxies, small galaxies with black holes in them, merged together and made bigger galaxies, and then also made bigger black holes. And so that process happened over a long period of time, and so we end up with all of these merging black holes. And so that should leave a signature of gravitational waves that we should be able to detect right now. And those detections will allow us to say something very important about the conditions in the early universe and the nature of the galaxies that were forming at that time. What's another reason that we might want to search for more? Well, here's one that involves both the millisecond pulsars and the youngest pulsars. And that's to do with the exotic physics of the interior of the neutron stars. So just to remind you that neutron stars have this mass of around about 1.5 times our sun. And so if you possibly could grab 1 teaspoonful of neutron star material and hold on to it, it would weigh as much as 1 billion elephants. And this is just an opportunity for me to show lots of photos of lovely elephants that I've managed to meet on trips to South Africa in the past. And so these objects are incredibly dense, and it means that there's some really exotic physics happening inside of these neutron stars that we cannot access with laboratory experiments. It's just impossible. You can see here, this is a cartoon of a neutron star. It's not to scale. The crust areas are, of course, much smaller than the innermost regions. But you can see there's an outer layer, or there's an atmosphere, we believe. These objects have an atmosphere. Then they have a so-called outer crust, which has got a lattice of nuclei with a density of 4 × 10⁻11 grams per cubic centimeter. It's just incredible density. And then as you go further in, the density gets greater. You enter these so-called pasta phases where things are stretched out and distorted in their shape. And then right in the next layer, the so-called outer core, we get individual protons present, but mainly we've got neutrons. 95% of the matter in this region is actually neutrons, and hence we got the name neutron star. And then right in the very center, we don't still know what's there. It could be quarks, or it could be strange baryons, or it could be some other exotic physics that we don't yet know. So how do we access that? Well, one of the ways to access that is people make models of the equation of state. And the equation of state just says, in very simple terms, it says, how does the mass of an object change with radius, okay? And so these lines that you can see here, all of these curved lines, all correspond to different models for the equation of state. And it depends on the very detailed physics of these objects. And these other lines on here, it's showing different Hertz values, correspond to what is the maximum speed you can rotate at given this mass and this radius before material will just fly off your neutron star, okay? And so you can see 1500 Hertz, 1250, 1000, and then 716 is here for a reason, because this corresponds to the fastest spinning neutron star that we currently know about, okay? And so this spins 716 times a second. And you can see that it doesn't really rule out many of these different models for the equation of state. Okay, you'd have to have a speed of something like 1250 hertz before some of these models are no longer possible, right? You can't have this mass and radius because it lies to the right of these purple curves. So these millisecond pulsars give us the opportunity to constrain it via their rotational period. So we want to find more systems, hopefully systems that spin even faster than the so-called this pulsar. How do we get the masses of these objects? Well, we can get the masses via the general relativistic effects, which you've encountered earlier today. You can also get the mass if you manage to find a pulsar in a system with a optical companion, and then you can measure the velocity of the optical companion and also therefore constrain the orbital parameters to get the masses. And the plot on the right-hand side shows you all of the neutron star masses that we've measured so far. And you can see that there's a handful, was it 3 or 4, 5, which are apparently beyond 2 solar masses. Okay, so the maximum mass that we've measured for a neutron star so far is up at around about the 2 and a bit solar masses. But you can see most of them have pretty large error bars on them. So what we want to do is we want to take that plot that we had just before, and we want to also put a mass limit on it. And if we do that, here I've put a conservative mass limit of, say, of 2.1 solar masses on here. And you can see that it starts to rule out some of these equations of state. And so we know that this model, for example, is not able to make a neutron star, which has a mass of 2.1 solar masses, independent of whatever the radius of the object is. So we want to find more of these pulsars so we can measure their masses and therefore also constrain the equation of state. Okay, so in conclusion, there are 3 main ways to find radio pulsars, and each has their benefits and disadvantages. So a combination of all 3 is the best. There is often a choice we have to make between targeted searches and all-sky or blind searches, and it really depends on what your aims are and how much observing time you've got available. I touched on just a couple of reasons why we should search for new pulsars, but there are dozens more, and I'm sure Marissa has already touched on some of them as well. And if you're interested in knowing any more about this field, then please do not hesitate to get in touch. Thanks very much.